Hello friends, welcome to my channel. Let's have a look at problem 1973. Count nodes equal to sum of descendants. In this video, we are going to share a solution based on recursion. First, I'll read through the statement to digest the problem requirements, and then we share the idea and explain the codes. So first, the statement. Given the root of a binary tree, return the number of nodes where the value of the node is equal to the sum of the values of its descendants. So here a descendant of a node X is any node that is on the path from node X to some leaf nodes. The sum is considered to be 0 if the node has no descendants. So here are three examples. In example 1, so the output is 2. So here is the explanation. For example, for the root node 10, so the left subtree have a sum that is 6. Right subtree have a sum that is 4. So 6 plus 4 equals 10. So we get 1 counting. Then for the subtree rooted at the node with value 3, so we have two leaf nodes, 2 and 1. They are also single node trees. So 2 plus 1 equals 3. So this subtree is also a valid 1. So we increment the counting by 1. So we get 2. So this is example 1. So in example 2, so we have such a binary tree. So you can examine that there's no tree such that the node value equals its descendants value sum. So the return is 0. So in example 3, so the return is 1. So this is actually a very special one. So there's a single node and the node value is also 0. So in this case, we're going to return 1, right? The reason is that if there's no left subtree and right subtree, so we regard that their corresponding sums are zeros. So 0 plus 0 equals 0. So we return 1. So however, if the root value is not 0, then we're going to return 0, right? So this is example 3. So before we look at the idea, let's look at the constraints. So the number of nodes in the tree is given by the closed interval, so 1 and 10 to the power 5. So in other words, the tree overall is not null, and the number of nodes is bounded above by 10 to the power 5, which defines the problem set's upper bound. Secondly, the node value is non-negative, and it's bounded above by 10 to the power 5. So with that said, so we are ready to look at the idea and the coding. So here we are going to use recursion. The reason we are going to use recursion is that it's effective here, and also so when we meet problems with binary tree, the binary tree itself can be defined recursively, or in other words, it's a recursive abstract data type. So recursion is a natural suit. The idea is very straightforward. So for each tree node, which also represents a tree, right? So we compute the tree sum value corresponding to every node. In the process, we could update the condition. So for example, if we examine a tree rooted at node, if node value equals the left subtree sum plus the right subtree sum, then we're going to increment the counting by 1. So as we are going to compute the tree value sum, so here is a sum, let's write it. So the recursion relation is actually very simple. So let f so compute the tree corresponding to node, the sum, right? So the tree node value sum for the whole tree. So this is our interpretation. Then we get f node equals node value plus f node left plus f node right. So in plain English, it means that we want to compute the tree node values sum. So we're going to compute the root value and then compute the value corresponding to the left subtree and corresponding to the right subtree, and then add them together, right? So that's the simple recursion relation. So with that done, so we are ready to look at the coding. So the coding actually, so for in order to make it effective, we're going to introduce an attribute. Let's call it self-result. That's going to do the counting, right? So we are going to write a helper function to do the above job for each subtree node. For each tree node, we're going to compute the tree node value sum corresponding to that tree node or the corresponding tree. So in the process, actually, we can do the update for this result. So now let's look at the helper function. So I can call this function f. So if you pass a node to this, the function f will compute the tree sum corresponding to the tree represented by the node or root. So in the process, we want to do another thing, that is update the attribute self result, right? So this way, as long as we finish writing the helper function, we just need to make a function call and then return the final state of the attribute. That's it. So with that said, let's first treat an edge case, or not edge case, a base case. So if not root, so in this case, so we are going to return 0, right? Because there's a null tree, so the corresponding sum is interpreted as 0. So this is more, we are using more like a stop condition for our recursion call, right? So in other words, it's a base case. So with that done, so actually we can get the left and right subtree sum, that is f root left, f root right, and then so in the process we are going to do a check, right? If root value equals left plus right, and then this node corresponds to a valid counting, so we're going to increment the result by 1, the attribute by 1. And next, what we're going to return is root value plus L plus R. So that's the f itself actually did two things. First is compute the node value sum, and also in between we do updates, right? This updates actually is what we devised. So with that said, actually we can call this function. So we can call this f root. So this function returns the tree value, but we do not implicitly use this for the return. So let's use dummy thing. So next we are going to return the self result, because once we call this function, so this attribute will be automatically updated during the recursion process. So that's it. So this actually forms a complete format of solution to this problem. So now we are ready to do the check. It passes the first example. Now let's look at the generic case. It passes all the generic cases. I guess that's about it for this specific problem. Actually here the problem logic is sort of straightforward. So we will stop here for this video. Thank you.